Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. In my channel, I deal with the different aspects of mathematics, physics and chemistry, and also in biology and other related topics. We also do some application questions, especially on these various topics or subjects that I've mentioned. And of course, we can check in a link in various description boxes of videos, and also check the related content which we normally do. So today we're going to look at an aspect of the radioactive decay, and this basically is the concept of a beta decay. And in this specific discussion, we're going to concentrate much on the aspect of conservation laws, and we have talked about the concept of conservation laws in some of our videos, of course, which basically we have mentioned as some of the laws which are going to ensure that the fundamental laws which are in place for other aspects of especially the general reaction, chemical reactions, and other areas of transformation are observed. So we had talked about the concept of energy, whereby we said that in a nuclear reaction, the total energy is going to be conserved. And also we said that there are some aspects like linear momentum that we had spoken as one of the, this is a momentum, as also another aspect which has to be conserved. And also we said about the concept of angular momentum, which also fall under this specific category of conservation laws. And also we talked about the aspect of mass. Also the total mass of that specific system has got to be conserved. And also we mentioned the concept of charge. We had said that charge is one of the aspects that is going to, of course, affect these specific conservation laws, whereby we are going to see that we can be able to represent these various aspects using the initials or symbols that we're going to see later being used in our discussion. So these are some of the laws which we had mentioned, and particularly for today we're going to look at the concept of angular momentum, which is going to be experienced under the concept of beta decay. Now, in our generic illustration of the concept of beta decay, we have said that we have two fundamental aspects in beta decay, which is beta negative and beta positive for negatron and positron emission respectively. And this, of course, can be illustrated using a general case of a decay of an atom or an radioisotope, which is going to be generally given as X. And the transformation for a beta decay is going to occur with an addition of a 1, of course, unit for the atomic number, the mass number, the atomic number, and then we're going to see that the mass number is going to be maintained. And this is going to be accompanied by the release of a beta particle. And of course, later I'm going to mention the concept of an antineutrino given as such. So in this specific case for the beta decay, insofar as the conservation laws are concerned, we're also going to see that this aspect of angular momentum that I've mentioned is going to be experienced in the aspect of beta decay. And this is going to be in contrast with the alpha decay, which we have said is basically the release of a helium nucleus given as such. So for the alpha decay, there is a transformation of a mass, which we had given for the mass number by a change of 4. And in the beta decay, we're seeing that there is a net change in mass, and therefore we're going to look for other aspects like the angular momentum, which are going to affect this aspect of the fundamental conservation laws. So therefore, for the beta decay, since there is no involvement of mass, we are going to see that the equation must obey the conservation law, especially the conservation of angular momentum. And this is going to be the difference between the total spin of the reactants and the product. Now, in a discussion about the quantum numbers, we had mentioned the aspect of a spin, whereby we said that in our description of the configuration for various elements, we had said that electrons have they can either assume a positive or a negative spin given as such, and we're going to see these specific aspects playing a role in order to ensure that the stability is maintained and this aspect of conservation of laws, of course, is maintained. Therefore, the difference between the total spin of the this specific product and the reactants. So in this case, if you consider this one a general equation to be like a chemical equation, we're going to have this one acting the role of a reactants, or a reactant in case if it's 1, and this is going to act as a product on the right side of this specific nuclear equation for the beta decay. Therefore, we can be able to consider the change in spin of this specific general equation, if this is to represent the change in spin, by taking the product minus the reactant for that specific aspect of a spin that we have mentioned. Now we can be able to find the total spin for the, whereby we are going to see that the if we have a general equation or 137 transformed to barium 137, and then there's of course accompaniment of this beta and negative decay given as such. We're going to see that this is 55, then this is going to be 55 plus 1, which is 56. But of course, we are concerned with the change in mass, which is of course is not having a net change in mass. Therefore, we're going to consider the aspect of angular momentum as I've mentioned. So therefore, we're going to consider the spin of the products and the reactants, whereby the sum of the spin of this specific isotope product and the beta decay are going to be given in terms of values, whereby we are going to have the spin of this specific barium 137 being illustrated as 11/2. And also we're going to have the spin for the electron, which is a beta product given as half. So the total spin for the product, these are going to be 12/2, which basically is going to be an integral number, which is 6. So this is going to be the spin of the product. So excluding this, so I'm going to consider this specific spin up to this particular level, which is the product of this radioisotope product and this beta decay. So we're going to have the spin of these two products given as such, which is 6, of course, in number. And then the spin of the reactant, which is cesium 137, is going to be 7/2. So this is a given value. There's a specific way we're going to consider this in trying to find the spin of various isotopes as we have mentioned. So therefore, this is going to have this specific value for the reactants, and this is going to be the product. Now, if you try to consider this one, then therefore, we're going to find the difference in the spin by minusing, by finding the difference in the spin of this specific, we have said it's the product minus the reactant. So therefore, the total spin is going to be the difference between this specific product minus the reactant, which is basically 6/1 minus 7/2. So that is going to be, we find the common factor here is 2. So this is going to be 12 minus 7, which is 5/2. So for us to ensure that the loss of the conservation, so this is total spin of that specific reaction. So for us to ensure that the conservation of this specific law of angular momentum is observed, the whole spin has got to be an integral number, which is basically going to be a whole number. So therefore, in finding it to be the total of 5/2, this means that if the angular momentum has not been observed, this particular product is not going to be stable if it is going to be given as this specific daughter nucleus and then the beta decay. So there has to be another, of course, product which is going to be given in order to ensure that there is a conservation of angular momentum, as I had mentioned later. So this is going to be in consideration, going to give us an aspect of considering this aspect of the neutrino, whereby we are going to see that this specific additional product that is going to be given in order to ensure that a loss of conservation of angular momentum are observed is going to be referred to as the neutrino, and it's going to be symbolized using that specific letter for V. So sometimes we're going to find another designation V with a specific symbol, this specific upper part. This is going to refer to as anti-neutrino. And we're going to talk about that one later. So this particular particle is going to consist of the value of a spin over half. So its spin for this specific neutrino is going to be a half. So this is the spin. And then we're going to see that it's going to have a charge, a net charge of 0. And therefore, and also the mass is going to be approximately 0. So therefore, we're going to see that this aspect of a spin, which is having a quantity of a half, will cause an effect in this product side. So if we try to consider this one, therefore, by adding this aspect of a neutrino, then therefore we're going to see that this specific number for the spin is going to allow for conservation of angular momentum, whereby we're going to see that for the product side, we're going to have the spin as I've said of this daughter nuclide, which is 11/2, plus the spin of an electron, or the negative beta, which is basically an electron, is going to be a half, and then we're going to have the spin of this neutrino being given as negative half as such. So this is going to give us 13/2 for the product side. So that basically these three products are going to give us a total spin of that one. Now for the reactant side, we had said that this spin is basically going to be 6. So in finding the difference between 13/2 minus 6/1, so this is going to be given as so this basically was 7/2 for cesium, where we are given the example of a cesium undergoing a beta decay and the resulting the formation of barium-137, a beta decay, and an antineutrino as I mentioned. So basically this is going to consist of this specific so perhaps if I may try to just give it in a clear way so that we can be able to avoid confusion, I'm going to do away with these notes now that we have discussed about it. So I've said the general equation that we're going to use for this is cesium-137. This is going to undergo a beta decay and result in the formation of barium-137 given as such, and then we're going to have this beta negative, which is an electron, and then we're going to have an antineutrino given as such. So therefore, as we said, if we have these two specific products, we're going to see that the total spin is going to be, as we had calculated, a 5/2, which basically is not an integral number. So an integral number basically refers that we need a whole number in this specific case for us to balance the total spin for this, whereby we had said that cesium-137 is going to consist of a spin of 7/2, and then these specific products are going to consist of a spin of 5/2. The difference between these two, of course, are going to give us a specific value. And then we had said that we can be able to balance off this one by including this neutrino effect, which has got a spin of a half. And therefore, this specific neutrino has got no charge, it has got no mass, and therefore we can be able to see that this is going to be a 6/2, and the difference between, so sorry for that. So this one we're going to see that we can be able to find an addition of the product side, whereby we can add this spin for barium. We had said for barium-137 it's going to be 11/2, and then for the electron it's going to be a half, and then so that correction, we have to make that correction for that. So we're going to see that the total spin of this specific side for the product is going to give us 13/2. And then we have the spin for the reactants, which is going to be 7/2. So the difference between this spin for the product minus the spin for the reactants, as we said, is going to give us 6/2, which basically is going to give us an integer value, which is going to be 3 given as such. So this is going to be a whole number value, an integral value, which is going to be a whole number value. And this, of course, is going to allow us observe the law for conservation of angular momentum, as we said, and this beta decay process. So therefore, this is going to be a general illustration for the reaction, or rather the decay process for cesium-137 being given as such. So from the first illustration for the general case we had given, whereby we had omitted this one, under the conservation laws, then therefore we're going to see that we have to include this specific product for us to observe those conservation laws. So this is an addition to the first one we discussed on the alpha particle, and therefore go and check on that specific video that I'm going to put in the link, and kindly subscribe to our channel so that we can be getting updates on the related content, especially on the topic of radioactive decay. So that is it for now, guys. Kindly catch us in our next videos. We're going to look at other aspects of radioactive decay and the concept of decay energy, as I've mentioned. So that is it for now, guys. Bye, God bless.